Now let's look at the periodic table, and what we'll do is eventually tie this into our discussion of electrons and how we can use the periodic table to help us figure out bonding patterns. So here we have the full periodic table, but I'm going to go through and highlight the atoms that are of the most interest to organic chemists. So of course, we care about carbon, and we also care a lot about hydrogen because hydrogen is often bonded to carbon. And we also will be using most of the atoms in the same row as carbon. So boron, nitrogen, oxygen, and fluorine. In fact, we'll be using all the halogens, FCl, Br, and I. Occasionally phosphorus and sulfur. And then in a few cases, we may use a group 1A or 2A metal. We have a couple instances where we use magnesium and then the ions, sodium, lithium, and potassium. For the most part, that's about it. In organic 2, we'll be using a few of the transition elements like copper and palladium. But really, the organic chemist's periodic table is pretty limited for the atoms that we actually use. So a few trends that you should have learned in general chemistry, but we'll go ahead and review. The first is electronegativity. This is a trend we're going to be using quite a bit. And the main thing to keep in mind is electronegativity increases diagonally toward fluorine. So maybe I shouldn't have covered F up completely, but that is the direction in which electronegativity increases. So electronegativity is just, in simple terms, an atom's affinity for electrons. So a more electronegative element or a more electronegative atom likes electrons more than a less electronegative element. The second trend is atom size. And as you go down a column on the periodic table, you increase in atomic size. Something else to remember about a group on the periodic table, so a group is just a column. Remember that atoms in the same group will have similar chemical properties. And that's going to be especially true when we start talking about reactions. Many of the reactions that we'll do with chlorine will also work with bromine and iodine. So, and then when we talk about countercations, lithium, sodium, potassium, those are all very similar. So in terms of how we're going to apply this to bonding and really talking about electronegativity, things that like electrons, things that don't like electrons, we can kind of split the periodic table down the middle. So just to give us a little more space, I'm going to hide the lanthanides and actinides. And you might remember from general chemistry that the atoms in group 5A, 6A, and 7A, these tend to gain electrons to become more stable. So that's why in the ions you would have F minus, O minus 2, N minus 3, things like that. But then on the other side, in groups 1A, 2A, and 3A, we're not counting our transition group. These tend to lose electrons. So that's why lithium will lose an electron, become lithium plus. But what we find is this column in the middle, group 4A, that contains carbon. And carbon really doesn't like to gain or lose electrons. Carbon really falls right in the middle. And because it doesn't really like to gain or lose electrons, instead, it likes to share electrons. Because it shares, carbon plays nice with other atoms when bonding. And that's why we have such a vast array of chemistry associated with carbon compounds.